Hi, this is John, and this is my second video assignment of Fundamental of Semiconductor Device 2. And for today's video, we're going to talk about the Fundamental of Semiconductor Device 1. So, I will explain with Fundamental Semiconductor Device 1's table of contents in my course material. But I'm not sure that I can explain it perfectly, so I think we can study together in this video with those materials, you know? So, we're gonna start. So, in the first course material, we have a free electron in one dimension, electron in infinite potential well, and EK diagrams, and reflection and transmission, and tunneling. And for the first and second part, we learn about the Schrödinger equation to interpret the electron's behavior, how electron moves in one dimension and in infinite potential well. So after that, we can learn about the energies and K's relationship, so we can draw EK diagrams about it, right? And after that, and so we can study it with the graphs, maybe. So in the case of free electron, EK diagrams look like this. So as you can see, it's not quantized, right? So, and the main point is free electron can have non-quantized energy, a continuous energy. But however, in the infinite potential well, electron have a quantized energy level. And so, after that, we learned the reflection. We learned about the reflection and transmission and tunneling, that is the movement of the electrons in potential well and those spaces. So, so that was a third material, and I think my fourth material is vanished. So I think I have to see PDFs in here for sure. So we have a electron in the finite potential well in hydrogen atom, energy levels in silicons, and energy bands for the table of contents. And the most important part of this was energy bands, right? So, and the most important thing in the energy band part was a definition. So we're gonna talk about the energy bands with the new material. Yeah, so there's a lot of concepts in here. I don't know if you can see, but yep, there's a conduction band and forbidden band, also called as an energy band gap, and the valence band. So let's talk about the definitions of those concepts. For valence band is the highest energy level that fully occupied of electrons in 0 Kelvin. Yeah, so thermal condition is an important part in 0 Kelvin, and the conduction band is energy band, the lowest energy band that is empty. There's no electrons. It's called a conduction band. And between them, there's an energy band gap. That means there's no states that electrons can exist. So it also called as a forbidden band or forbidden gap. And there's a energy vacuum level that is a kind of standard line, standard point in a vacuum state. And there's a two concepts, and one at the left is a, I think you can't see, but it's a electron affinity. That's a difference. That's the difference of a conduction bands to a vacuum energy level. And the right one is a ionization energy that is from the valence band to a vacuum energy level. So this was a definition and a concept for to interpret and draw a band gap. Band gap, yeah, that's a band gap. So this is the most important part of my fourth course material. And for the fifth, there's a pseudo-classical mechanics for electrons and EK diagrams in 3D crystals and conduction band, valence band structures, and effective mass. So for the pseudo-classical mechanics, we have to learn this because in real world, it is hard to interpret how the real electrons behavior, yeah, how electrons move. We we're gonna use the classical mechanics to interpret the electron's behavior. So that's the concept of this contents. And those in 3D crystals, EK diagrams, we can see the picture, I guess. So, where's the 3D crystal? Yeah, EK diagrams of 3D crystals. So left one is gallium arsenide's conduction band and the valence band, and right one is a silicon's conduction band and the valence band. So as you can see, the conduction band and the valence band's edge is at the same point in this energy band diagrams. So the electrons can move from conduction band to the valence band while not losing a crystal momentum. But in this, like a silicon, as you can see, the conduction band and the valence band is located at the different position. So if the S size electron from the valence band wanna jump to the conduction band, and they have to change their crystal momentum. So this this case is way harder to for the electron that jumps from conduction band to the valence band. So that's the EK diagram of 3D crystal. So let's go back to a table of contents. And there's a important part what's called effective mass. So we're going to talk about the effective mass right now. Effective mass is a concept that includes every relationships and every power that affects to a real electron that is in the semiconductor, in the material. Because there's so many relationships and force that affects to electrons in semiconductors, so we can't figure it out and we can't explain all of those concepts, so we just include every relationships to a one concept, and it's called effective mass. And that's the point of the fifth, I guess, the fifth course material. And we're gonna move to the sixth material. We can see intrinsic and extrinsic semiconductor and density of states and Fermi-Dirac distribution and electron and hole distributions. So, intrinsic semiconductor. For the first, intrinsic semiconductor is a pure semiconductor. So, in intrinsic semiconductors, for the electrons concentration in valence band and the hole concentration in conduction band is same in a thermal equilibrium states. So that's the intrinsic semiconductors. And if we put a dopant, dopant atom like donor and acceptor, and it changes to extrinsic semiconductors. So if we put a donor atom in an intrinsic semiconductor, so it's a donor, right? It's a donor, so they give the material, the donor atom that we put in an intrinsic semiconductor gives electrons to a semiconductor. So there's way, I'm sorry, so there's, uh, so they have way more, so they have electrons concentration way more than a hole concentration. So we call it as an N-type semiconductor. And if we put an acceptor and they get electron from the semiconductor, so the semiconductor can be a P-type semiconductor because its hole concentration is way bigger than electrons concentration. So it was a extrinsic semiconductor, and the next concept is a density of states. Density of states is the number of states that the electrons can exist. So it's kind of like a number of rooms in hotel. It might be way easier to understand. And Fermi-Dirac distribution is a probability distribution of the existence of electrons. So so we also have to know why we have to learn those two concepts. It's because so the main point of the semiconductor is the current that flows in the semiconductor. So if we want to know how much the current flows in semiconductor, we have to know the carrier's concentration, right? So if we want to know the carrier's concentration, we have to use those two concepts. So I think I used so many times, but never mind. But so density of state, we're gonna multiple density of states in Fermi-Dirac distribution, and we're gonna integrate those two multiplications. Then we can get a carrier concentration, and if we can get a carrier concentration, we can calculate the carrier's current. So that's why we learn those two concepts, right? And the last thing is electron and hole distributions. This might be conduction bands, the electrons concentration at the conduction bands, and holes concentration in valence band. And for the last part, the seventh course material, we learn electron and hole distributions in extrinsic semiconductor and compensation and charge neutrality and carrier concepts with temperature and band gaps with the temperature and lastly, degenerated semiconductors. So, uh, if we so extrinsic semiconductor, it was a semiconductor that is which is the dopant dopant. I mean the donor and acceptor is added. So I said what I said before. The concentration of electron and hole is different. So when in n-type semiconductor is the majority carrier is electron and minority carrier is hole. And in p-type semiconductor, the majority carrier is hole and minority carrier is electron, right? So when we put so by the difference between the two carriers, so in n-type semiconductor, the Fermi energy level is going higher than the intrinsic energy level, that is the mid gap of the band gap. And in p-type semiconductor, the Fermi level located way lower than a mid gap, the intrinsic semiconductor level. So we can draw a band gap of extrinsic semiconductor with those relationships. That's what we learned in this part. And for the next one was the compensation and charge neutrality. I mean, and this is uh, this is a case that if semiconductor has an acceptor and donor both, and we just learn how we can calculate the minority carrier with mass action loads, as you can see in here, right? And the next one is the carrier concentrations versus temperature. And we learn in this part we learn the relationships between carrier concentrations and temperature. And so for the conclusion is when the temperature gets higher, the intrinsic semiconductor carrier concentration is getting higher also. Right? That's because if the temperature gets higher, the electrons can jump way more the way more from valence band to conduction band. So the conduction bands the conduction band's carrier concentration, I mean the electron concentrations will be larger, will be bigger than before, and also the carrier concentration of will be higher when the temperature gets higher. And the next one is band gap versus temperature. So we can see the figure directly. When we can see this, when the temperature gets higher, the band gap's getting narrowed. It's called band gap narrowing. So when the temperature gets higher, the band gap narrowing awkward, and so the energy gap that the electron from valence band no I mean the electrons from valence band can jump to conduction band way easier than before. That's the main point of the part in band gaps versus temperature. And for the last one, the degenerated semiconductors, it's a semiconductor that is heavily doped by the donor atoms. So so when we heavily doped a donor or a acceptor, so it means a n-type and a p-type semiconductor. When we doped when we added really high concentration of those donor, then in n-type semiconductor, as you can see, the Fermi level penetrates to a valence band. So the Fermi level will position way higher than a conduction band. I'm sorry, excuse me. And in p-type, semiconductor, the Fermi level penetrates to the valence band region. So the Fermi level will be located way lower than the valence band. So this is the concept of the degenerate semiconductors.